Okay, so exponential functions. We are heading back into some graphing. I think surprisingly, even though exponential functions are not linear functions, they're not just like straight, right? Whoosh, just a straight line. They're this weird curvy thing. I think you might actually, maybe, just maybe, find this even easier than when you first learned linear functions. We shall see. So, what is an exponential function? Well, an exponential function is a function in this form: y equals a times b to the x. A and b are real numbers, right? And a can't be 0, or else that would just be a constant function. And b cannot be 1, or else that would also be a constant function, actually, because 1 to the x is 1, right? So it has some restrictions. Now for a cringe joke. Here we go. So parent functions are something that we're going to learn more and more about a lot in Algebra 2, and we're going to I label this, the book we're using in my classes doesn't actually call it the parent function in this lesson, but it's a good idea to kind of go ahead and get that terminology in now, I think. And so here's the cringe joke. You ready? Exponential functions are the only functions other than logarithms that live in a two-parent household. It's not a very good joke, but it's a joke. So most, like the linear parent function, is just this, right? Except without the little weird thing, right? That's a linear parent function, y equals x, right? In a unit or two, we're going to learn about the quadratic function that looks like a parabola. So most functions just have one type of parent function, but exponential functions have a growth parent function and a decay parent function. Now, what are parent functions? We'll get more and more into that, especially in Algebra 2. We'll kind of look at it in that way. But a parent function is kind of a template, right? So with exponential functions, with functions with this equation, you kind of start with, when you're thinking about, well, what is this going to look like? You're going to start with one of these two things. So for growth function and decay function, both, they have that same template function, y equals a times b to the x. The difference, and the biggest difference on the top bit, is the domain and range, you notice, is the same, but the equation for this, now a has to be greater than 1 on both of them, right? It has to be, it can't be, greater than 0. And so it can't be a 0 and all of those things. For a growth function, b has to be greater than 1. So 2, 5, 20 million, 2.3, right? Something that's bigger than 1. But for a decay function, it is b, the one that is raised to the x, has to be something between 0 and 1. So we're talking about things like 1/2 or 2/3 or 0.589237, right? So anything that's between 0 and 1, not including them. So that is how you get the one or the other, right? So the domain and range are the same. They go from negative infinity to positive infinity on the x for the domain. So it can be another way to write that, of course, is all real numbers, right? All real numbers. So basically anything, right? But the domain and that's true for both of these. And the range has to be greater than 0. Now you notice when you look at this, it's not abundantly obvious. When we do the example, we'll put some numbers to it, and it'll make even more sense. But both of these functions, they, on one of their ends, so for the growth function, it's as x decreases, the function's getting closer and closer to 0, but you notice that the range is y is greater than, not greater than or equal to, right? It's just greater than. So this function, as x goes down, it's going to get closer and closer and closer and closer and closer and closer to 0, but it's never going to quite touch it. Same thing for the decay, but it's as x increases, the function decreases. So it's getting closer and closer and closer to 0 over on this side, but it's never quite touching it. So the word for that, a line on a graph that the function gets closer and closer and closer to, but never quite touches, that is called an asymptote. I'm not going to spell it on this page because it's in the example that we're going to see in a minute. So an asymptote is a line that a function gets closer and closer and closer to, but never quite touches. All right, so let's take a look at the example. So here we go. We're going to graph y equals 3 to the x. All right, and turn off notification sounds. Fix it right now. Here we go. Fixed. Done. All right, there we go. So we're going to graph y equals 3 to the x. We're going to find the y-intercept, so where the graph crosses the y-axis, and state the domain and range, and the equation of the asymptote. So where does it get closer and closer and closer to? So what we're going to do for this, we're going to kind of learn a technique that it's important to think about. I think I've changed the wrong brush. I have, in fact. It must be a keyboard shortcut. I should figure that out. That I accidentally did. So the way we're going to do this, the way we're going to graph y equals 3 to the x, is we're going to use a technique that we used before when we were first learning linear functions that is important to learn because it always works. Like if you can do something like this, which is relatively simple, then you can honestly get some graph for something that's really complicated, like y equals x minus 2 times x plus 3 times 24 over x minus x times x plus 8. You could graph this right now using the technique I'm about to show you. Now, it's helpful if you know what the parent function is supposed to look like, so you can have kind of a instinct for what this is going to look like. But using this method that we're about to do, you can really get some version of a graph for everything, pretty much anything, right? And that is simply, we're going to draw a t-chart. So x and y, and then we're going to fill in the t-chart. Now, even though I say this in videos and whatever else, often I'll still get the same question. So I'll say it as clearly as I can. For the x values, for what we're going to put in for x, you just pick numbers. Okay. So what I like to do is start out with just -2, -1, 0, 1, 2. And if that gives me enough information by itself, then I'm good to go, and I can just connect those dots, and I've got a pretty picture. If I get those in there and it's like, that doesn't really quite tell me enough, then I can do a few more points, and then I can connect the dots. So let's do that for this particular graph. Let me shrink this a little. So y equals 3 to the -2. So we're just substituting these x's in for x and getting an answer. So this equals that we can actually put in the calculator. Now, you know that what this is going to do is it's going to flip it over. So it's going to be 1 over 3 squared, right? So you could put this in the calculator, but this is pretty easy to do, right? 3 squared is 9, so 1/9. So 1/9. Now, if we compare to our growth and decay function, this is the a, right? So, or excuse me, this is the b. The b raised to the b is the one that's raised to the x. And b, in this case, is greater than 1, so this is going to be an exponential growth function. So it makes sense for, if I plug in a negative number, for it to be a little number over here. Right? So that answer so far makes a lot of sense. Right? Let's do to the -1. Y equals 3 to the -1. Now we know from exponent rules that flips it down to the bottom. So this would be 1 over 3. 1/3. We plug a 0 in there. That's easy. I'm going to go ahead and write it out just for the sake of notes and clarity and all the things. 3 to the 0. Anything to the 0 is 1. So this is 1. Now it asks for the y-intercept, right? That's the y-intercept, right? The y-intercept is when x equals 0. So it's where it crosses the y-axis. So it's 0, 1. So we've got our y-intercept. That's great. -1 and 1/3 is about right there. -1 and 1/9 is right there. So we're already looking like a really straightforward exponential growth function. So we're going to put a 1 in there. So y to the, equals 3 to the first. Well, 3 to the first is easy peasy. That's 3. So this is 3. I can go ahead and put that on there. 1, 1, 2, 3. And then I'm going to substitute a 2 in there. 3, squared. 3 times 3 is 9, so 3 squared is 9. 2, and the 9, and 9, which is actually up here, right? That's pretty much, since we have the parent, that's enough information to be getting on with, right? Then we're going to connect these dots as best we can. It's easier on actual paper with more resistance. I'm doing an okay job. That'll work. So there's the graph. The y-intercept is the point 0, 1. The domain and range, the domain is negative infinity to positive infinity, because it's what x can be. The range is y is greater than 0, right? The equation of the asymptote is going to be y equals 0, right? Because y equals 0 is a constant function, and it looks like this. Let me get a slightly different color. So that would be this. Y equals 0 is a horizontal line right there. So there's the asymptote. Y-intercept, all those things. And for now, we'll learn more in Algebra 2 and in Pre-Cal and all of those places. But for now, that's what you need to know about exponential functions and graphing them. We're going to get a little bit more detail on some specific types of growth and decay functions in the next lesson. But for now, that's it. Easy peasy. We'll see you in the next one. Do your homework, all the things. Ask questions in class or in the comments below, whatever else. Have a good day. Bye-bye.